Hello everyone, I'm Hassan. I will present our work on human-like planning for reaching in cluttered environments. Imagine grasping a tub of yogurt at the back of a cluttered fridge shelf. This is an easy task for humans to do. Even very young children can do this. We may think of high-level questions like whether to directly reach the target or firstly to push some objects away. Reaching directly, which path to go through, and pushing an object, which one and where to. Such high-level questions are not addressed by the standard robot planners, which are based on random sampling, high-dimensional with increasing the number of objects, and so they suffer from limited object manipulation and long planning time. We aim at learning high-level planning skills from humans and transfer such skills to robots. This is an overview of the Human-like Planner (HLP), which runs in two phases: the training phase, shown by the green arrows, and the testing phase, shown by the yellow ones. I will go briefly through these steps. Firstly, we collect a dataset using a virtual reality setup. In virtual reality, we ask human participants to pick a target at the back of a cluttered environment. Collecting this data, we have pairs of training scenes and human trajectories. The problem now is how to segment these demonstrations. This is not a trivial problem because in each trial, the positions of the objects are randomly shuffled. We introduced a novel way to model the task space. This row-based structure is used during all the training scenes in VR. The start and target points are fixed and aligned at a straight line. Two rows of cuboid objects with three objects in each row. We used qualitative representations to model the task space. For example, a gap is the free space between two objects at the same row. We have two actions in the action space: going through a gap and moving an object. The part of the free space that is used to connect between rows is called a segment. To move an object, we discretize the space around it into 8 directions. For example, FR is forward right, BL is back left, and so on. This structure is fixed during all the training scenes in VR, but we will show later in the experiment sections how to generalize beyond this. Given a training scene like this, we locate the objects and the gaps, and we have the ground truth human trajectory. We can see that in this case, the participant decided to go through the gap G2 at the first row and move the object O6 at the second row. And this is the high-level plan, which is a sequence of key points in the action space connected by segments. After segmentation, we have state action pairs that can be used to train the decision classifiers. Decision classifiers are trained to answer the high-level questions raised at the beginning of this presentation. Which gap to go through, which object to move, what is the direction to move an object, and which segment to select. The training phase is now completed, and we end up with trained classifier models that are the building blocks of the HLP algorithm. The algorithm is run in the testing phase. Given an environment, we locate gaps and objects, run the gaps and objects classifiers. So we have candidate gaps and objects. These candidates can be connected between rows with combinations of segments. So we run a regression model to estimate the human arm configuration with each combination of gaps and objects between rows. And we compute the expected collision associated with each path from the first row to the second row. Finally, we output the high-level plan as the path with the least expected collision. This high-level plan can be transferred to any robot model by connecting it to a robot-specific low-level controller, which computes the IK solutions required to move the robot joints. To evaluate HLP, we did experiments using Mujuku physics engine with a benchmark called STO, Stochastic Trajectory Optimization, which is a real-time online replanning algorithm. We can see how HLP can outperform the benchmark in terms of both success rate and planning time. In the real experiments, you can see how HLP can think over the free space around the objects in a way that's similar to how humans think, so that it can pick the target faster than the STO, which is biased towards its straight line initialization between the starting and target points. Please note that we generalized beyond the training structures. The starting and the target points are not aligned. The number of objects in each row is different, and also the shape of objects are not the same as that used during training. We tested HLP with increasing the number of objects, and we found that, as you can see in the paper, that the actual planning time is almost fixed, regardless of increasing the number of objects, which prove the scalability of the HLP algorithm. We increased further the number of objects, and also the rows here are not nicely structured as that done during training. Even with having to push some objects, not just going through a gap, the proposed HLP is faster than STO because it doesn't suffer from increasing the number of objects. In conclusion, we learned from humans interacting in virtual reality, and by using qualitative representation of the task space and action space, we were able to generate a high-level planning algorithm which is scalable with the number of objects and can be connected to any robot model. Our future work includes generalizing beyond the raw structured environments using more powerful classifiers like shallow or deep neural networks and using a closed loop planning algorithm. Thank you.